we can think a little bit more now about endothermic reactions and how they're possible, because it is a weird thing. You know, it's a system in which energy is kind of taken in from the surroundings and used to promote something to a higher energy level. So it's the equivalent of, if I let the pen go, of it not dropping to the ground but it rising up into the air. So it's a weird thing, and the reason it's possible has to therefore be to do with entropy changes, because in terms of energy it doesn't seem to make sense. So let's see how that works. So the first thing is to remember what we have established, which is that delta G must be negative for a feasible reaction. And yet, if a reaction is endothermic, then delta H is positive. So you can see that that's unhelpful, right? Because what it's saying is that the answer has to be negative, but we're starting with a positive number. And so, taking that into account, you can easily see that the only way that could possibly be true is if minus T delta S, so minus T delta S must be negative, and therefore T delta S must be positive. Right, so if minus T delta S is negative, then T delta S must be positive. Sorry, the dog was just making his contribution there. So minus T delta S must be negative, T delta S must be positive. And remember that T is positive by definition because it's the absolute temperature. So T is positive by definition. And if T is positive and T delta S is positive, then delta S must be positive. Okay, and that's the important result, that delta S must be positive for an endothermic reaction to be feasible. And that's the important conclusion, that yes, you can have endothermic reactions, but only if they're accompanied by an increase in entropy. And that's a very important result. So if you think about a sort of typical example of an endothermic process in chemistry, if you heat something like calcium carbonate, it decomposes into calcium oxide plus CO2 gas. And that's a strongly endothermic reaction. You have to heat it to very high temperatures to provide enough energy for it to happen. But you can see that it's also a reaction that's going to have a positive delta S because it's producing a gas, so it fits in with this definition. So that's an important result. What we can also do is sort of think about what the effect of changing temperature will be on the feasibility of an endothermic reaction. So a very important type of graph which you need to be able to think about and deal with goes like this. So if we have the temperature in Kelvin, so the absolute temperature along there, so starting at 0 and going up, and then if we put delta G on here again with 0 in the middle there. So let's first of all think about absolute 0. If the temperature is absolute 0, then T is 0, and therefore this whole term will disappear, right? Because 0 times anything is 0. So at absolute 0, when T is 0, delta G just equals delta H. Okay, and for an endothermic reaction, that will be positive. Okay, so we can put that point on there and say delta G equals delta H when T equals 0. Okay, you should be able to see why that's true just by looking at this, because if T is 0, that whole term vanishes. So delta G is delta H when T equals 0. And that's it's positive, therefore, for an endothermic reaction. And if delta G is positive, that means it's not feasible at that temperature. However, what you can also see is that once we start to increase T above 0, this term appears and gets bigger in magnitude as T gets bigger. So T is positive. We've said delta S must be positive for an endothermic reaction, so we're subtracting a positive number times a positive number. So in other words, we're subtracting a positive number, and that means delta G will do that as the temperature rises. And you can see there comes a point when it crosses the line. So above this critical temperature, delta G becomes negative, and then the endothermic reaction becomes feasible. So what this graph shows you is why endothermic reactions tend to occur at higher temperatures, because they're only feasible above a certain critical temperature. Okay, so we can just label this to make that point, that delta G is positive, greater than 0 in this region, which means that it's not feasible. But above this critical temperature, we get that delta G is less than 0, so the reaction is now feasible. So this kind of graph is quite important for showing why an endothermic reaction only becomes feasible above a certain critical temperature. So if we call that temperature T min, the minimum temperature at which the reaction becomes feasible, the next stage is going to be to calculate it. So this is the minimum temperature at which reaction is feasible. So let's see now if we can do a bit more rearranging of our delta G definition and figure out how to deduce what T minimum is. Just thought I'd interrupt this briefly just to show you how riveting the dog is finding this discussion of entropy and free energy. Okay, he's been like that throughout so far, so I hope you're finding it slightly more engaging. What we can see from that graph, okay, remember it looked like this, that if this was delta G and T in Kelvin, this was the value of T minimum is what we want to find. And the point is that at that temperature delta G is 0, because it's just going from being positive to being negative. So what we can say is that that equals 0 when T is equal to T min. So we can therefore rewrite that as delta H minus T min times delta S is equal to 0. And therefore delta H is equal to T min times delta S, and therefore delta H divided by delta S is equal to T min. So that's quite a useful relationship, because it lets us calculate the temperature at which an endothermic reaction should become feasible. As always with these things, you have to be very careful with the units, make sure they're compatible. But this is something that you are quite likely to need to use, so you either have to learn it, or just look at that and think, yeah, all you do is set that equal to 0 and rearrange it. It sort of depends how comfortable you are with that little bit of rearranging. So either learn this, or just remind yourself how to quickly derive it. Okay, so let's look at an example of that. Here's an example of an endothermic reaction. So delta H is positive, which is what tells you it's endothermic, and you can see that it should be feasible at some temperature because delta S is positive, and we said that's the requirement for endothermic reactions to be feasible in some temperature range. So we can plug those numbers into the expression we just derived, which is that delta H divided by delta S is equal to T minimum. And as I say, we just got to be really careful with the units here. So delta H is plus 80 kilojoules per mole, so delta S has to be in kilojoules per Kelvin per mole, so the kilojoules are compatible, and at the moment it's not. So again, like we were doing earlier, we have to divide that by 1,000. So that becomes plus 0.140 kilojoules per Kelvin per mole. So we'll just write the units on to remind you why we did that. Okay, to make the units compatible. And if you compute that, you get that T minimum is 571 Kelvin. And as you can imagine, what they're likely to do is ask you to put it in degrees C, just so that you have the extra step. So that's equal to 571 minus 273, which is 298 degrees C is T minimum. So what it's saying then in the context of this graph is that that is 571 Kelvin on there. So the reaction is not feasible at temperatures below that, so it wouldn't happen at room temperature, which is about 293 Kelvin. But if you heat it up enough, you reach that critical temperature, and above that the reaction is feasible. Okay, so we can say reaction is feasible above 571 Kelvin. Again, the proviso before, remember, feasible doesn't necessarily mean it will happen. It could still have a hugely high activation energy, in which case the rate may be negligible, but it's not being stopped in terms of the fundamental enthalpy and entropy issues. Okay, so the final thing that is worth doing is to look at these same kinds of graphs for other situations. So the one we've already looked at is an endothermic reaction, so positive delta H with a positive entropy change. And we saw that taking account of this equation, that gives you feasibility, but only above this certain critical temperature. So let's consider the other possibilities. So if we just draw a graph down, a line down there, let's consider what would happen if we had an endothermic reaction with a negative delta S. And again, what we do is do all our thinking in terms of the definition. So everything to do with free energy, you need constantly to be referring to the definition, which is that. So let's see how that would work out. So we can draw the same kind of graph. So again, when T is 0, at absolute 0, that whole term vanishes. So delta G is equal to delta H, which is, as we said, positive. Once we move above absolute 0, this term appears, and T, remember, is always positive because absolute temperature can't go below 0. So this is a positive number, but delta S, we've said, is negative. So we're subtracting a negative term. And if you subtract a negative number, you add a positive number. And that means that delta G will get bigger because we're adding a positive number onto this number that's already positive. So the graph will go like that. And of course what that means is that delta G can never be negative because it's going to be positive at all values. Okay, so that just says graphically what we'd already stated, that delta G is positive for all temperatures, which means the reaction could never happen. So that reinforces what we've already concluded, which is that delta S must be positive for an endothermic reaction. Let's then consider, what about exothermic reactions? So let's take the example of delta H being negative and delta S being positive. Okay, and then we'll squash the other one in a minute. So delta H is negative, delta S is positive. So here's our graph, delta G against temperature. T is 0, that term vanishes, delta G is equal to delta H, and now we're saying it's negative at that point. But as the temperature rises, this term starts to appear. Delta S is positive, and therefore we're subtracting a positive term, so we're adding a negative term, and therefore the value gets more negative. So the graph is going to look like that. So you can see this time we have kind of the opposite situation from this, which is that delta G can never be negative. No, try that one again. Delta G is always negative. It can never be positive, and therefore the reaction is always feasible. It's feasible at all temperatures. Okay, so delta G is negative for all T, which means that it's feasible at all temperatures. So if you had a situation where delta H is negative, so an exothermic reaction, and delta S is positive, then you don't have to worry about the temperature because it's always going to be feasible. So let's do the fourth case. So again an exothermic reaction, but this time with a negative delta S. And you can probably guess what's going to happen this time, but we'll go through it anyway. So when T is 0, this term vanishes, delta G is equal to delta H, which is negative, so again it's starting down here. And then as T is cranked up, this term appears, and delta S is negative, so we're subtracting a negative term. So minus of a minus is a plus, so in other words we're adding a positive term onto this, and as T gets bigger, that positive term gets bigger, and so we get a line that goes like that. So this time, again we have a critical temperature, but it's the other way around, that below this temperature, so we'll call this T max, because below this temperature, so delta G is less than 0 if the temperature is below T max. In other words, it's feasible up to T max, but above T max delta G becomes positive, and so it's not feasible at higher temperatures. So we get this interesting situation that for lots of exothermic reactions they're actually only feasible up to a certain temperature, and then they stop becoming feasible. And so you can calculate Tmax in exactly the same way we calculated Tmin for an endothermic reaction, because that same relationship will hold, that Tmax is equal to delta H divided by delta S. And in this case you'll get a minus, a negative delta H divided by a negative delta S, and again a negative divided by a negative gives you a positive temperature, so that's fine. Okay, so that should be all the background you need. What remains now is to practice and practice and practice to get all of the classwork questions done, and then as you get further into your revision you'll find lots of examples coming up in past papers, and there are some specific entropy and energy questions identified by topic on the VLE as well, so lots of practice that you can be doing.